We introduced this idea of the fast step being in equilibrium and writing that the rate in the forward direction equals the rate in the backward direction. And that is a condition for reaching equilibrium. So maybe it's a little new. We haven't done our equilibrium chapter yet, but we're going to use that. And so on this page, I had written the rates in the forward and the reverse directions as equal. So that's how we'll handle those fast equilibria sections. That allowed us to rearrange and get rid of the intermediate, because we can't test a rate law by changing the initial concentration of intermediate. So we have to get that intermediate out of our rate law, and we can do that with that fast equilibrium and rearranging it. So let's give that a try on this one. So I like to write the rates for each step and then work with that just to sort of lay it out in advance, but whatever works for you. So we assume that the first one reaches equilibrium and it's fast, right? Our overall rate is going to be equal to the slow step, right? So that'll be rate number 2 for step 2. I took note of the intermediates. Those are the things that are formed and then consumed. So they don't appear in the overall reaction. So we might start by writing the rate law for the slow step, but that has an intermediate in it, so we can't use that experimentally. Yeah, so we'll write the rate for number 1. So we'll write it in the forward direction. And because that's a fast step, it's going to reach equilibrium before the slow step can even be measured, essentially. So those will become equal. Now, given that these are steps in a mechanism, what are we assuming about them? We are assuming that these are elementary steps. That means that our rate is written as the stoichiometry. Right? The hope with a mechanism is to propose something that is a series of elementary steps of how things actually react together, in which case that stoichiometry would be valid. But here we have our intermediate, so we'll need to get rid of that. And then we'll square root both sides. All right, so then we're going to plug that into there. I'm going to rewrite this as just a new constant, k prime, just another value, just to group it together. And now we have a rate law that we can test experimentally, right? We can do the method of initial rates, change the initial chlorine, change the CHCl3 concentrations, and verify this rate law. And if it does check out experimentally, then maybe this is the mechanism. If it doesn't, then we have to throw our mechanism out and try again. Okay, questions on that? How did it go?
Is the K sub -1 just indicative that it's the...
So that's the K in the backwards direction for step 1.
So with this one, do we have to look at step 3?
No, step 3 doesn't come into it because that happens after the slow step.
Okay. If step 3 had been the slow step, would we have to go through all 3 steps?
Yes. So if step 3 was a slow step, then you would have an intermediate, and then you'd have to use the previous step, and then you'd probably have intermediates in that, and you'd have to substitute again. So it's a little more complicated. We could look at, let me see what the worksheets, it's been a while since I went through this content up, but down under course resources, I do have a mechanisms no key.
Would we ever encounter a reaction that has multiple slow steps?
There's usually one that's going to be slower. So, I mean, if you think about pouring things out of bottles and you have 2 different bottlenecks, one of them is going to be rate limiting. So that's the one that will set our rate.
So the slowest is the rate of the whole reaction.
Yes, the slowest one will give the overall rate. So there are a couple. This one gives you a rate expression, and then it gives you some potential mechanisms. So you might need to figure out which could be consistent. Here they give you a rate law and then asks you which is rate limiting. Yeah, so there's a bunch of different problems, 6 more practice problems. So once again, those are under course resources, worksheets.
That's okay.
But down below, lecture slides just for extra stepping through it. Some extra reading on linear regression. Equilibrium, now would be a good time to take a look at the crabapple war. Maybe I'll open that up. But then farther down, these are the other worksheets, kinetics, practice, and mechanisms. And then math review for equilibrium. I think that's a bunch of quadratic equations. And it has a key. Okay, so just a quick tour of some of the resources there to help. And we will go back to catalysts. Just a few things that we need to know about catalysts. They're kind of like an escort. They provide an alternative pathway. So sometimes that can be helping things find each other, or it could be connecting with 2 parts of a molecule and putting strain that pulls it apart. So geometry considerations are a big factor, but it lowers the activation energy. So it provides an alternative pathway. And the other thing is they're always regenerated. So you can use a really small amount of catalyst because it's not consumed in the reaction. So vitamins, for example, are catalysts. A lot of our biological reactions would not take place in a reasonable timescale for life if we didn't have catalysts. If we have a homogeneous catalyst that has the same state of matter, so these are both, these look like they're all aqueous phase. And you can see how it has this high activation energy right here. But then in the catalyzed version, it breaks it up into easier steps. So they all have lower activation energies. So where does the H plus add here to make it easier?
With, yeah, the HO, the hydroxyl group, it looks like.
Right there, that one. The O that has the OH on it already. Okay, in step 1, the Lewis base. Oh, Lewis acids and bases. Have we talked about those? Have you studied those?
Mm-hmm.
Oh, okay, cool. Great.
Yeah, we studied them.
So the Lewis base is the one that's going to donate the electrons, right?
Yeah.
So Lewis acids and bases are defined as lone pairs, donor and acceptor. So the donor is the base, and the acceptor is the acid. Because I usually work with Bronsted-Lowry acid bases where the acid donates a proton.
Yeah.
Instead, we look at the lone pair and we look at the bonding electrons. It's accepting those electrons. So yeah, the O on the OH. And then the H plus is accepting that lone pair. Okay, what bond breaks or forms after that binds? That is the CO bond, right? Right here. So that means we have water as a leaving group, which you'll see a lot of that in organic, right? So it leaves that water molecule. So what process is easier because of the catalyst?
Decomposition, it looks like.
Yeah. Catalyst gets regenerated from there. Really, it allows that.
Would be the carbon-oxygen bond breaking, specifically in that molecule.
Yeah, and then that HCO releases that catalyst back up. All right, so which one is rate determining? We have this value. It looks like that second step is the higher energy. So yeah, I think the CO bond breaking in the second step. Breaking in step 2. Yeah, because it added the hydrogen on the carbon. Oh, that was already there. And then when it releases that hydrogen as the third step, it's a little bit easier. Okay, because the activation energy is higher. So as a heterogeneous catalyst, then we have something in a different phase. In this case, it's a solid catalyst surface. And it takes that 3-dimensional gas or liquid down to just 2 dimensions, so they essentially find each other faster. They adsorb onto the surface. Then that reaction on the surface is a little easier, a little faster. And they find the C2H4 molecule for that reaction. So here's the profile. Oh, yeah?
Oh, sorry. Is that what adsorption is? Just where it binds to a surface?
Yeah.
Okay.
So it has that large activation energy based on the collision rates and the orientation and the energies. But then on the surface, it lowers that activation significantly. And the surface probably stabilizes the octet deficient carbon. It provides something that's there that helps stabilize that. All right, so which one's the rate determining step?
Surface reaction. Yay, biological catalysts.
Yeah, biological catalysts. So these tend to have a larger active sites. It's more than just a couple molecules. There's several different areas of geometry that give that lock and key sort of fit. And they're often highly specific. So this is showing that sucrase. So that big blue molecule is just a lot of atoms. It's a macromolecule. And we have a binding site for the ring while it's together. And then the blue has a conformation change that puts strain on that bond and makes it easier to break it. Right, so it breaks that down more quickly. And then this is another macromolecule rendering where you don't see the atoms at all, but the little strings are the strands, and then the flat parts are where they're in the helical coils, so you can kind of see the different structures, the secondary structure in this kind of a rendering. All right, so conversion of oxygen to ozone catalyzed by nitric oxide. We have a series of reactions. So show the overall reaction, identify intermediate catalyst, and so let's take a minute to do that. Moiety, in general, means a part or a portion, especially a lesser share. So that was interesting. Their anthropology definition came up first in terms of groups of people, groups of like cultures. And then I clicked on the chemistry definition, and it's a distinct part of a large molecule.
I always interpret it to mean like a functional group.
Well, that would work pretty well, right? Because that's a distinct part. So for the overall equation, we're going to add these together. That's it.
For if we see it just written out like that, and we're not told one of the things is a catalyst, how would we distinguish it from an intermediate?
Yeah, we can tell by looking. You don't have to be told that.
Because there's no nitrogen compounds in our final reaction equation there.
Well, neither of these are going to show up in your overall.
I think the catalyst is the one that you were putting on. So it should be like the reactant put in, not like a product.
Yeah. So neither of them really show up in the equation. An intermediate is defined as something that what?
It's formed and consumed.
It's formed and then consumed. Okay, so those are going to be NO2 and O. These are intermediates.
See it now.
Is consumed and then reformed or regenerated. So it interacts with a molecule and then gets kicked off at the end. It still cancels out of the overall equation. Okay, so the catalyst here, this one's the catalyst because it's consumed first and then regenerated. So NO2 is the intermediate and NO is the catalyst.
Dr. G, is it safe to say the catalyst just happened in the first step of the reaction?
That's true. It just catalyzed the very first step. It just got it started. Yeah, so you can see how those work together. Without the NO, the oxygens wouldn't be able to form that NO2. Yeah, so that's it, right? That's the end of our kinetic stuff. Except for the lab tomorrow.
Yeah.
So have you guys looked at the pre-lab quiz? Yeah, it's a lot about the procedure, which I think will help in terms of knowing what to do with the data. It's only 10 points. Oh, good. There's no time limit. In this case, I'll just have you write it up, use your notebooks for your work, and then write it up, write a report. So this one will be a formal report, and then submit that report a week later.
For lab notebooks, if we can find a good, like, sort of PDF or format it well, would an electronic one be easier?
Part of the goal is to have a written diary, because no matter how much you use a computer, I mean, it seems like, I guess it's been a while since I've been in an industrial lab, but we did everything on paper. And if I did something on the computer, I would make my Excel chart, I'd print it out, and I'd tape it in there. I'd recommend just using one of these.
Okay.
And then you can just follow the instructions just as it says. Then you have paper you can write down. I'm going to give you data. And you
Yeah.
can write down into your notebook what you have. And not everybody's going to have the same data. I've got several sets of data.
Right.
The lab, the data collection is
Uh-huh.
relatively short in this sequence. So really, like when we do the acid base lab, you have like 5 values that you write down, and the rest is just calculations till the cows come.
Okay.
Do you care if we use spiral bound notebooks as opposed to the composition ones?
Well, I mean, technically, it shouldn't be something that you're ripping out. Technically. But, I mean, to be completely realistic, of course, I'm not collecting these from you.
Sure.
Right? So part of my idea is that if you have a really good notebook, sometimes that really, you can bring it with you on interviews, and you can show that. And you can say, even online labs, I still maintain this skill. So it's a little bit more flexible than it would be if I was actually collecting the thing.
For the pre-lab, it said to include properly labeled data tables for the effect of like concentration, catalyst, temperature. So you have any idea what it's supposed to look like?
Yes. Okay, so if we go into the lab 1, that's going to pop it down into this block. And then there's the note sheets, the lab manual pages. And then I gave you the Excel version of table 1. So that's probably not going to open here. So let me stop that one. And I gave this to you so that you can use it to modify. So this is what's given in the lab manual. So you could notice a couple things. I put my title in the table so that it won't ever break across pages. So I'm going to copy all that and just paste it again.
Oh.
And then you can just easily update this, make this table 2. And then this is going to be concentrations, for example. Your titles, your table titles should usually be descriptive. They might even match the segments, the headings in the lab manual. So
Okay.
if you make this concentrations, then you could say, here it says 0.02, but really we want it, you can write it over here, 0.012 molar, and then you have 0.2, and that's the milliliters. It's always good to over-designate, over-label everything. And then here you could say, okay, I'm going to just make that equal this times that. Oh, and it's millimolar. Do we want millimolar? We probably have to divide by 1,000, right? Boom. And then, well, actually, if you set this up actually originally so that you reference this one up here for your concentration, then you can just go like that. Oh, but you know what happened? We've got to hold this molarity still. That I'm going to put $signs around that one. And that says, even when I drag my cursor, keep that one in the same box. And then that way you can drag it down like that. Now, another thing that happened is my formatting changed because that dragging takes the formats with it. So you can reformat, you can make it look the way you want it to. But does that help you get a sense of how useful it is? It looks really nice. These ones with the double lines maintain that formatting because it's really clear. But I just messed that up. So I might take this outer box and say, okay, I want that to be, oh, not quite. Oh, I'll just take this one because that has the double bottom border. I don't know, it's not perfect. But hopefully you get the idea. I gave you that Excel table to start with so that you can play with Excel and streamline your calculations. Yeah, I mean, it's an important skill. It's helpful. Like, you have to know how to do the math, sure, show your work. But in your notebook, you can show one sample calculation and then do the rest in Excel. The trick with Excel, though, is if you make a mistake, you have to find it. You have to know it and find it. And then here, maybe we want to change this display and look like scientific notation, number, scientific. There you go. That's a little cleaner. And then, so for tomorrow, have those data tables on paper, or if you're, on paper so you can write down the data.
Okay.
I'm not sure how I'll structure that assignment, but basically it'll be an assignment to be there and get that data, and then that's it. There may be 1 or 2 questions because I have to assign points in order to make an assignment. But then the post lab is where the points for this lab will be. It'll be a full report with the standard formatting due in 1 week. And that one will be a file upload.
That's
Will we
true.
be submitting like images of our written work with the formal report?
You have a couple choices in the calculation section. You could use an equation editor and make it look beautiful. It's very time consuming. I say that because I remember thinking nobody would spend that much time, and then I realized that my whole career is all about formatting and thickening lines and staying up to midnight making beautiful pictures. Okay.
Oh, I actually enjoy that kind of work as like a break. It's relaxing. It makes me feel like I'm getting something done that's important, and it's like low stress.
Yeah, and then 5 years later, you look at it and you're like, wow, I was a hotshot. So it's worth doing. It's worth doing. If you don't want to do that, or your computer's not working, or you didn't leave enough time and it's stressing you out, you can handwrite in the appropriate section. You can handwrite the sample calculations. They have to be clear and readable. They have to be large enough that I can see them. They have to scan okay. Right? So try to make it formal, but you can handwrite them if you don't have the equation editor. And you don't have to do all the repetitive calculations, just one of each kind as a sample.
For the calculation section, should we put just like the general form of each equation that we use, or an actual example with real figures from the data set?
You'd use the actual figures from one of the trials in your data set and use one that works. So if there's faulty data, don't use that in your sample calculation.
Sure. Cool. Thank you.
Not have a great afternoon.